All right, this is going to be the solutions to the Unit 1 pretest for AP Calculus AB. This is going to be on limits, continuity, and differentiability. All right, so the first problem, and I should label these, this is problem number 1. We have this graph here, and it tells us that it has vertical tangents already, and it tells us that we have vertical tangents at -1, -1, so right here, and at 1, 1, right here. It also tells us nothing else, just it's asking where is f not differentiable. So notice that also right here we have a sharp corner. Sharp corners are not differentiable. What are the 4 things that makes a function not differentiable? Let's list them. So the first thing is sharp corners. Sharp corners. The second thing, we have discontinuities. So this is, I'll do a little note here. This is going to be holes, gaps, breaks, or a vertical asymptote. We also have, what else? We have endpoints. And finally, let's see if you guys can get the last one. It is vertical tangents. These are the things we're looking for, and we found a sharp corner and we found 2 vertical tangents. There's nothing else in this graph. So at x equals -1, so I'll circle these 2 at -1. I should do a different color here. Come on now. At we have -1, 1, and 2. Those are our answers. So our answer is D. D. Come on now. All right. So that was problem number 1. Let's go on to problem number 2. I'm going to label this problem number 2. All right. So this is a limit problem. When I take the limit as n goes to infinity, or as anything goes to infinity, I'm really asking for what? I'm really asking for the horizontal asymptote, and I can write that down here. So really looking for, what am I doing here? I'm just going to say HA, horizontal asymptote. And when we take the limit as x goes to infinity, when we're looking for this horizontal asymptote, we are using our top-bottom rules. So review on top-bottom. Oh, what am I doing here? Top-bottom rules. And hopefully you know these. So you have case 1, case 2, and case 3. So case 1 is, oh, I should actually make these farther apart because I know that these are going to be fractions. Case 2 and case 3. So the case 1 is where the top, or the exponents on the top are bigger than the exponents on the bottom. So bottom is lowercase. And that is not this case because both of these exponents happen to be the same. So I'm just looking at the largest exponent here. I should make that clear. Case 2 is the bottom. What am I doing here at bottom? The bottom is bigger. So the degree is higher on the bottom than the top. And the final one, they're both the same. So the top and bottom have the same degree. Okay, it's hard to talk and write at the same time. This is going to be bottom. So what are these equal to? Go ahead and give yourself a chance to review. What are these equal to? Top is bigger. That's going to be infinity. And this means it does not exist. All right, where the bottom is bigger, this is always 0. Top is the same. This is going to be magic fraction. Magic fraction. Magic fraction just means I take the coefficient of the largest degree. So in this case, the top is the same degree as the bottom. So you take the coefficient. Coefficient is 3. Coefficient is, there's an invisible 1 here. So it's going to be equal to 3 over 1. And therefore the answer is D, using our top-bottom rules. Let's move on to problem number 3. So I'll label this problem number 3. All right, limit as x goes to 0. So what happens when we plug it in? The immediate thing you should think, just plug in 0. Plug in 0 and you will get 0 over 0. There's 3 things you always do when you get 0 over 0. What are they? Give you a second here. First thing that you do is you factor. Second thing is eliminate. And lastly, you should know this as well, sub it back in. So let's go ahead and factor it. So if I factor that this function, so I still have my limit as x approaches 0, and this is going to be, I can factor out an x squared that is the greatest common factor of the numerator, and this is going to be a 5x squared on the inside plus 8. And for the denominator, I can also factor out an x squared that is the greatest common factor, and on the inside I have a 3x squared minus 16. Okay, I just did step 1. This little check mark should be bigger. Step 2, eliminate. So here we go. I'll do this in a different color. All right, those are eliminated. Check. And finally, sub it back in. So when I sub it back in, I'm subbing 0 back in. 0 goes into x, 0 goes into x, and I'm left with 8 over negative 16, which simplifies to negative 1/2. So the correct answer here is A. All right, moving on to question number 4. So this is question number 4. We have a function that is continuous, so it already tells us it is, and it's defined by this. So what is b? All right, so whenever we're looking for b when we have a function that's continuous, there's going to be 3 steps. So step number 1, and I guess 1 and 2 can be reversed in any order, but I'm going to say that this is sub in suspect point. Step 2, set the left equal to the right, and this should also be equal to the point, and I'll do a little star here in a different color. So sometimes the point will be the left or the right. In this case, take a look right here, this less than or equal to, that is the point, so it is the left. I don't have to check the point because it is the same thing as the left, so I really only need to check that the left is equal to the right. So let's go ahead and finish this up and get the third step in here though. Third step is solve. All right, so let's do step 1. So step 1 is to sub in the suspect point. So on the left, I'll label these, and on the right, the left, if I sub in 5 into all of my x's, I get 5 squared plus b times the quantity of 5. And this is going to be, I'm setting it equal to, I'm doing step 1 and 2 all at the same time. Watch out here. This is going to be equal to 5. I subbed in 5 for x. I can put parentheses to let you know I subbed it in. All right, so simplifying this really quick, I'm going to subtract 25 from both sides. So I have 5b is equal to negative 20. See if you can follow that math there. And then finally divide both sides by 5 to get negative 4. So b is negative 4. Kind of funny that this is problem number 4, but the answer is not 4, it's negative 4. Again, these 3 rules whenever you have a function that's continuous and you're looking for a variable that's not x in here. Moving on to problem number 5. Label this problem number 5. So we know where the horizontal asymptote is. It's y equals 7. So which of these must be true? And I always underline true because sometimes it's false, so I'm just making sure these are, that means 4 of these are going to be false, 1 of them is going to be true. So what do we know about the horizontal asymptote? So list some facts. So I'm not even going to call it horizontal. I don't want to write it all out. I just want to say HA. This means I'm taking the limit as x goes to infinity, or it could mean I'm taking the limit as x goes to negative infinity. I'm going to one of those two. I think in the notes I just say plus or minus infinity, something like this in the notes. Limit as x goes towards plus or minus infinity. So it has to be one of those two things, and then that is equal to, I also know that the horizontal asymptote is equal to whatever number they give me. In this case, it's going to be 7. So horizontal asymptote is going to be equal to 7. So with these 2 pieces of information, I can solve my problem. So I know that it must be equal to 7, so I can cross out this, this, and this. And now I also know it's the limit as x goes to infinity, so it has to be the one that goes to infinity. And either or, like if you started with fact number 2, you could still eliminate all but 2, and then use a final piece of information to find the answer. But the correct answer here is E. The fact that x goes to negative infinity doesn't change the fact that it still goes to 7. Negative doesn't go to negative. The horizontal asymptote is still the same, even at the other end of the graph, at the left end of the graph. All right, let's take a look at problem number 5. No, it's number 6, I apologize. We just did number 5. So this is problem number 6. All right, we're looking for which of the following does this limit exist. What type of limit is this again? Is this left-hand limit, right-hand limit, or double-sided limit? You decide. And if you said it is a double-sided limit, you are correct. And what do we know about a double-sided limit? Double-sided limit. There are two things that need to be equal to each other. What are those two things? I know that the limit on the left needs to be equal to the limit of the right. And if you want the exact notation, like you were doing this for a free response, you would say that the limit as x approaches whatever point you're talking about. So we don't know. I'm just going to call a from the left, that means negative, needs to be equal to, or some function, I have to write that here. The limit of some function as I approach a from the negative side needs to be equal to the limit of the same function f of x as x approaches a from the right-hand side, from the positive side. So that's the notation. We don't really need that for this problem. We just need to know that the left and the right, they approach the same height. I should make a note here, maybe in a different color. This is the same height. And I don't care what happens at the value of 4. And I'll make a note here. I don't care what f of, we're doing f of 4 in this case, f of 4 is. I don't care what the height is. Anyway, I'm going to label this again, height is. I just want to know where it approaches. Just want the height that we approach. Keyword here being approach. I can spell approach. Here we go. Approach. So I don't care what's happening exactly at 4, but what happens when I approach? So the left here, this is really the limit of the left, gets closer and closer to the value of, this is 3. So the left equals 3 here. What about the right? So the left was coming this way, and the right is coming this way. So this is the right. Right also gets the similar height of 3. When these two are equal, then it exists. And not only does it exist, it's equal to 3. So both exists and is equal to 3 for this problem. So this one is good. Remember, we're trying to find things that exist. So check mark on number 1. Let's look at number 2. The left hand comes in here. It approaches the height of about 4. So I'm going to say left equals 4. What about the right? So the right comes up like this. The right approaches a height of 4. And again, you might think, oh, it doesn't exist because there's a giant hole here. That doesn't matter. Remember, I don't care what the value of f of 4 is. I don't care what the height is exactly at that point. I care what it approaches. And since they both equal 4, they should have an equal sign here. Not only does it exist, it's also equal to 4, so go ahead and give that a giant check. It does exist. All right, let's check number 3. So the left comes up like this. So this is left, and it seems to be approaching, I'm going to say about 4. And what about as I come down from the right? I should write 4 here. And right, this comes down and gets closer to about 2. So I'm going to put 2 here. 2 does not equal 4. When they do not equal each other, it does not exist. So this is a DNE. And not only is it DNE, it is a DNE, and therefore it's not existing. Remember, we're not looking for something, or we are looking for something that exists. It's kind of weird with my English here, but that one is not true. So no, yes, yes. We're looking for 1 and 2. The correct answer here is D. All right. Let's go on to problem number 7. All right, we have a graph. We're looking for where, for what x values, where c can be such that the height of the function, or the limit, the double-sided limit, approaches the height of 1. So again, double-sided limit, what do you know? The double-sided limit, we need to know if the left limit equals the right limit. And pictorially, that just means I don't care, again, what happens at the point. It could be an empty circle. It could be a gap. It could be, well, it can't be a gap. It can be a hole. But they need to approach the same point. I don't care what happens at that point. They need to approach the same point. If there's some break, then that's bad. That's bad. This is good. They need to approach the same height. All right, so let's take a look. So I'm going to draw kind of a, let's see here. I'm going to switch my tool here to a giant line at 1. So whoosh. Everything on that line, that's what I'm looking at, because I'm talking about the height of 1. So there's only 3 possibilities. I need to check that one, I need to check this one, and this one. Do those 3 double-sided limits exist? All right, let's check the first one. And maybe I think I'm going to erase my work here. Come on, grab the line. There we go. And get rid of that line. And in fact, I'll probably erase, no, I'm not going to erase those, but those are the 3 things I'm checking. So does a double-sided limit exist for x equals -2 at this point? If you're saying yes, you would be correct, because the left equals the right. They're both going to a value of 1. So this one is good. I'm gonna circle if it's good. I'm gonna cross it out if it's bad. Let's go ahead and check the value at x equals 0. Do they approach the same height from the left and the right? They do. So I'm gonna go ahead and circle this point too. It's a good one. What about x equals 3? You see here, it's a gap. It totally jumps. The left is equal to 1, the right is equal to, I don't know, half or something other than 1. Therefore, that one does not exist. This one is a DNE for the double-sided limit, so this one does not work. So my answer should be -2 and 0. Where's the -2 and 0? There it is, C. And I should have labeled this. This is problem number 7. All right, so let's go on to problem number 8. I'll label this problem number 8. All right, so we know it's continuous. Every time I see the keyword continuous or close or differentiable, I underline them because I know exactly, I know what theorem I'm allowed to use. There's 3 theorems. Continuous means IVT, continuous and closed means EVT, and differentiable means MVT. We can't use MVT is what I'm trying to get at here, because there's no differentiability. In fact, if there's anything trying to prove a slope, we can immediately just cross it out. So we're looking for something that must be true. Oh, look, there's a slope right here for E. That can't be the case because it's not differentiable. Go ahead and just cross it out. Oh, look, another slope. Can't happen. It's not differentiable right away. I mean, it might have an average slope of 0. In fact, it doesn't even give us a point, so it's doubly impossible. We don't even know if that point, or if the average slope is 0, since there are no points. So D and E are out of the question just because I don't see differentiable in this question. All right, what must be true? So let's go ahead and translate these. F of C equals 0. This means it crosses the x-axis. Crosses x-axis. You might also interpret this as the height of some point is 0. That is also correct. But we don't know if it crosses the x-axis. It might not. There's nothing in this problem that guarantees that it will cross the x-axis. IVT might guarantee it if it gave us points, such that this was in the interval of the x values and this height was in the interval of the y values, but neither of those things were given. So this might be true. It's not a must. What about B? We're down to between B and C. B says there's a number such that, okay, so this one can be tricky. We've seen this in the self-check. I think self-check 1.3 or 1.4 had this. This is saying that the height of some point that's between A and B, the height is greater than the starting point and it's less than the ending point. Not equal to. The key part here, there's no equal to right here. And here's the counterexample for B. So say you have a graph, and I have straight lines, but I decided to draw it. Say you have a graph, and it's a constant function, like y equals 3 or something. And let's say there's A, C, and B. C has to be less, or C, sorry, up here. The height of C has to be greater than A. This height right now, right here at C, is not greater than A. It's the same. And since this doesn't have an equal sign, we can't have this. This is also a might. So obviously our answer is C, since B was eliminated. But let's look at why C is the case. So we're talking about some number in that interval, and what does this guy translate as? One word, starts with an M, 3 letters. It is a max. Max exists because of what theorem? One of the 3 theorems. You should know this. Is IVT, EVT, MVT? It is EVT. Extreme value theorem guarantees maxes and mins as long as I have continuous and closed. So answer is C. Let's move on to problem number 9. Problem number 9. All right, so we have a function. Okay, so this is going to be a little bit tricky. We haven't seen something like this yet, but we have in our notes what a horizontal and vertical asymptote are generated by. So which of the following could be constants of a and b as long as it has a horizontal asymptote? I'm going to write here, this is horizontal, or we also know this as an HA in our notes. And this is y equals 3. The line, this line right here, this dotted line or dashed line, this is y equals 3. And then the VA, the vertical asymptote, is right here, this dashed line, and this is generated by the equation x equals 2. So the question is asking what a and b need to be in order to generate those two asymptotes. So let's take a look at the horizontal asymptote. I think we have more familiarity with this as of right now. Horizontal asymptote, HA, how do you make these again? It's the limit as x approaches something of a function. And if you said infinity, you would be correct. When I go to infinity, or negative infinity for that matter, I am going to get a horizontal asymptote. So let's do that. So I'm going to take the limit as x goes to infinity of my function. Right now I have ax squared plus 12 all divided by x squared plus b. When I take the limit as x goes to infinity, we are using our 3 rules. Do you remember those rules, or what they're called? They're called top-bottom rules, and we've reviewed them already on a previous slide. Top-bottom rules basically look at the highest degree. The highest degree is the only thing that's important. Everything else, just don't worry about it. Cross it out. We don't care. Highest degree here, we're looking at this term and this term. So highest degree, they're both the same. So if they're both the same, we're on case number 3, in which case we're doing a magic fraction. So I'm going to write here, this is equal to magic fraction. Magic fraction states that you take the coefficient of both of those terms and then make it into a fraction. So my fraction right now, again, there's a hidden 1 there if you didn't know. My magic fraction is going to be a over 1, which is just a. And since a is the horizontal asymptote, a must be this value that I'm given for the horizontal asymptote. A must be 3. So a must be 3. That eliminates c, b, and a. It's not negative 3. So I'm between b equaling negative 4 and positive 4. So lastly, I need to figure out my vertical asymptote, my VA. All right, this might be a little bit tricky. Some review. How do I generate a vertical asymptote? It has something to do with the denominator. That's your hint. So if you said set the denominator equal to 0, and that's all the places you will have a vertical asymptote, you will be correct. So I'm going to do that. I'm going to set the denominator equal to 0. So I'm going to put in here parentheses in case you want those notes. I'll say set denominator equal to 0. All right, so I'm going to do that. X squared plus b. I need to get this to be 0. And I know where my x is. My x is equal to 2 for my vertical asymptote. So if x equals 2, plug that in, I get 4 plus b equals 0, and therefore my b must be negative 4. If that is the case, then I'll have the vertical asymptote at 2. Yep, that all makes sense. So go ahead and it's not d because that's, or sorry, it is d. That is negative 4. And b is obviously wrong because it has the wrong value here. All right, let's go on to problem number 10. This is problem number 10. All right, so I need the limit as x approaches a of this. So whenever I'm taking the limit, I just plug it in. When I plug in a, I'll get a squared minus a squared. I'll get 0 on the top. If I plug in a on the bottom, a to the 4th minus a to the 4th, I got another 0. Whenever you get 0, you always, always, always do the same 3 steps. What are those 3 steps? Think about them right now. Oh, 1, 2, 3. Think about those steps. Make sure you know them before I tell you what they are. Step 1, factor. Step 2, eliminate. Step 3, substitute. Substitute back in with the same value. So let's do those. Do those in a different color over here. So I'm going to factor, and I am going to assume that there might be some of us that don't know a difference of squares. So let me go ahead and do that. So if I have something like a squared minus b squared, this is called a difference of, I'm going to just do a simple difference of squares. Look, there's a difference because there's a minus sign, and both of these are squares, difference of squares. So difference of squares, how does this work? That factors like this: a squared minus b squared. The rule states that this is going to be equal to a plus b times the conjugate, which is a minus b. All right, notice that in order to get these values, when I start over here, all I do is square root them. And if you go the other direction, that means in order to get backwards, I need to just square both of these values. In both of these cases, in the case of the numerator and the denominator, both of these are a difference of squares, but this one might be a little bit harder to grasp why that is a difference of squares, or it might be hidden to some of us that aren't experienced with it. All right, so let's go ahead and solve the problem. So I need to factor the top. I'm just going to go ahead and factor all of it. I know I don't need to factor the numerator because I've done this problem before, but I'm going to do it anyway, factor as much as I can. X squared minus a squared. How do I factor that numerator? So let me rewrite this problem. The limit as x approaches a of x squared minus a squared turns into x plus a times the quantity of x minus a. What about the denominator? I'll give you a chance to pause it and try to do this on your own. The answer here is x squared plus a squared, all of this times x squared minus a squared. And I'm going to explain this just a little bit because remember what I said up here. In order to get from this value back over here, I need to square each of these numbers. If I square x squared, I get x to the fourth. And if I square a to the I can't speak, a squared, I get a to the fourth. And vice versa. If I take the square root of x to the fourth, what I'm really saying is 1/2 of these powers, which is squared. That's why this factors the way it does. If you have questions, again, just please come in before or after school or at lunchtime. And you'll notice again, look at this. I have an x squared minus a squared. If I didn't factor the top, then I would have just been left with that and I could have eliminated it right from the get-go. But as I said, I'm going to factor this thing as much as I can, so I'm going to go ahead and factor the bottom as well. So I'm going to rewrite this problem. Limit as x goes to a of x plus a. I can't do anything in the numerator. I'm just going to rewrite the numerator, x minus a. But the denominator, x squared plus a squared, this thing cannot be factored unless you're dealing with complex numbers. And since all of calculus, as far as I know, is limited to the real domain, not the complex domain, we are not going to have to deal with him. X plus, if you have a sum of squares, don't worry about it. You cannot factor him. But this difference of squares, I'm using the same rule over here. So this x squared minus a squared turns into x plus a times x minus a. Now, I finally factored. It was a long factor, I agree. But number one is now taken care of. Let's do step number two. Step number two is eliminating. There's an x plus a, and here is x minus a, x minus a. We have checked off number two. We eliminated. Now all we have is on the bottom, so we're going to sub it back in. What is that going to look like? I'm actually setting this equal to. I know I'm going to the left here, kind of bad notation, but it is still equal to. This is going to be 1 on the top because there's nothing left, and I have a squared plus a squared. I'm just subbing back in a for x. And this, again, simplifies to 1 over 2a squared. So my final answer is B.